Okay, welcome back. This is 8.2, integration by parts. Okay, so what the heck is it? Well, it's kind of basically the integral of a product. So remember you had like a product rule when you took derivatives. So basically the derivative of a product is not necessarily equal to the product of the derivatives. It's kind of the same deal here with integration. And this is as close as we'll get to a formula for the integration of a product, a general formula for the integration of a product. Okay? So first we'll derive the thing, and we can use the product rule to derive it. So recall what the heck the product rule was. So maybe we have some functions of x, and we're taking the derivative of those functions with respect to x. So we'll call one u, the other one v. In order to take the derivative, you leave the u alone, and then take the derivative of v with respect to x, plus leave the v alone, take the derivative of u with respect to x. Okay. Let's integrate both sides with respect to x. Okay, so the integral of all that junk with respect to x is equal to the sum of the integral of these guys with respect to x. On the left-hand side, the integral and the derivatives kind of cancel each other out. You'll just have u times v. On the right-hand side, you'll have the integral of u, and you can kind of think of these guys as dividing out. So u dv plus the integral of v du. And then we can solve for the integral of u dv. So the integral of u dv will equal uv minus the integral of v du. Okay? And that's our formula. So it doesn't seem like it's the integral of a product, but the dv thing will be one of the terms in the product. So one is u and the other one's dv. But they'll both be functions. It's just you may not necessarily recognize that this is the derivative of some function. Okay, you'll just see a product of two objects. So anyways, let's take a look at how this thing works. What? Number 11. We have the integral of x e to the negative 4x dx. Okay. And yeah, we have the integral of the product of two functions. Okay, so we're going to let one of them be u. I'll let x be u, and then one of them let that be dv. Okay, so the rest of the junk we let be dv. So e to the negative 4x dx. Okay. In order to use this formula, I need to know v and du. Okay. So to get v, I did not make my box big enough. To get my v, I need to integrate e to the negative 4x dx. That should be a negative 4x, sorry. So in my margin, I can do the integral of e to the negative 4x dx. If you need a u sub, it will be negative 4x. So du is negative 4 dx. dx is negative du over 4. So this will become the integral of e to the u times negative du over 4. So that's negative 1/4 integral of e to the u du. So that's negative 1/4 e to the u plus c. So that's equal to negative 1/4 e to the negative 4x. Okay, so anyways, if I have dv, to get v, I just integrate this thing, and you'll end up with negative 1/4 e to the negative 4x. This is easier. You're taking derivatives, so du will be 1 dx. Okay. And then I can use my formula. So the integral of u dv is equal to u times v, so it's always this times this. So I have negative x e to the negative 4x all over 4. And then you go minus this times this, okay? The integral of it. So it's minus the integral of negative 1/4 e to the negative 4x times 1 dx. clean that up a bit, and we have some integration. Negative e to the negative 4x all over 4 plus, bring out the constant 1/4, integral of e to the negative 4x. I just did that in my margin. Okay, so that'll be easy. This is negative x to e to the negative 4x over 4 plus 1/4 times negative 1/4 e to the negative 4x plus c. And then that'll be negative x e to the negative 4x all over 4 minus 1/16 e to the negative 4x plus c. All right. And that's how it works. Okay. In general, there's an order kind of function types that will tell you which to use as your u and which to use as your dv. You can feel it out in general, and that's what I used to do when I was a student, but now we have kind of this formula that tells you which to pick, and it's the Leate formula. It's a section 3 Leate. So L for log, I for inverse trig, A for algebraic, T for trig, and E for exponential. Okay, and this tells you the order. So you're picking U first, and then you're picking V. So U first, and it's not V you're looking for, and then it's dV. Okay, so U first, dV second. In other words, if you have something like what we see in number 15, which is the integral of t ln of t plus 1 dt, you want your u and you want your dv, right? So your u, and we have two functions here. This one, t, is algebraic. So anything that's polynomial or just a constant, it's algebraic. So it has a square root, it's algebraic. And then ln of t plus 1 is logarithmic. Okay, so going back to our flow chart here, log comes before algebraic. So log is the u is first, and then algebraic must be your dv. Okay, so u is the log of t plus 1, and then dv will be your t. In fact is you couldn't, at this point, let dv be ln of t plus 1. That should be t dt, because you wouldn't know how to integrate it. So you're kind of forced to put your particular functions where they are based on what you know how to do. So I know how to integrate t dt. Our v value is just going to be t squared over 2. I wouldn't necessarily know how to integrate ln of t plus 1. I just don't know how to do it yet. But I can take its derivative, so I end up with 1 all over the guts times the derivative of the guts, which is just 1 all over t plus 1 times dt. Okay? Okie dokie then. Let's go ahead and do this integral. So it's always this times this minus the integral of that times that. So I have then t squared ln of t plus 1 all over 2 minus the integral of this times this. There's a 1/2 floating about. Then we'll have t squared all over t plus 1 dt. I could do long division to evaluate this thing. So t squared divided by t plus 1. So I'm thinking, what times t is t squared? Well, that's just t. And subtract. So I end up with negative t. And then what times t is negative t? So minus 1. And subtract. And you end up with positive 1. So doing this rotation, we can write our new expression for this integrand. What are we getting? T squared ln of t plus 1 all over 2 minus 1/2 times the integral of t minus 1 plus, so it's t minus 1 plus 1 all over t plus 1. Okay, plus 1 all over t plus 1. dt. I know how to integrate that. That'll be t squared ln of t plus 1 all over 2 minus 1/2 times t squared all over 2 minus t plus ln of t plus 1 plus c. And then you can go ahead and distribute the negative 1/2, and we have our final answer, t squared ln of t plus 1 all over 2 minus t squared over 4 plus t over 2 minus ln of t plus 1 all over 2, and then plus your integration constant. Okay. Okay, so let's, we want to keep looking at some of these. There's some weird things that happen sometimes. There's a shortcut formula, but you can't always use the shortcut. Okay? But we'll show you nonetheless. And other issues. For example, number 27 may sort of challenge you. Right? So the problem with this one, it's not clear that there's actually a product. Okay. And what is the product? So it's really, you just think of it as tan inverse times 1 dx. Okay, so one function is 1, the other function is tan inverse of x. So by Lie, algebraic, inverse tan before algebraic. So you're going to consider the constant 1 as algebraic. So our u value will be inverse tan, and then our dv value will be 1 dx. And again, we couldn't put inverse tan in here because I don't know how to take its integral. I'd just be back to where I started. Right. So anyways, v, the integral of 1 dx is just going to be x. And then du, the derivative of u with respect to x, and this is the differential form of the derivative. So we have 1 all over 1 plus x squared dx. Okay, so again, it's always this times this minus the integral of that times that. Okay, so I have x tan inverse x minus the integral of x all over 1 plus x squared dx. Okay, so anyways, I do a u sub to evaluate this integral. I'm going to need to go 1 plus x squared. Du is 2x dx, so therefore dx is du over 2x. Okay. So here I go. This is equal to x tan inverse x minus the integral of x all over u times dx, which is now du over 2x. So the constant that I can pull out is 1/2. I'll have x tan inverse x minus 1/2. The x's are gone. And then I have the integral of du over u. So this would be equal to x tan inverse of x minus 1/2 ln absolute value of u, and u in this case is 1 plus x squared, and then plus your integration constant. Okay, there it is. Let's look at one where we actually do an evaluation. So a definite integral. This is 41 in the book. I'm going from 0 to the pi over 4 of x cosine of 2x dx. So Lie says algebraic before trig. Right, so algebraic is u, dv is cosine of 2x dx. So taking the derivative of u, that's 1 dx. Taking the integral of cosine of 2x dx, that's going to be sine of 2x all over 2. Okay, so there's our chart. And then I want to go this times this minus the integral of that times that. Okay, so it's x sine 2x all over 2. I got to remind myself to evaluate. Minus the integral of, we could pull out a 1/2 and just have sine of 2x dx. This will equal x sine 2x all over 2 minus 1/2 times the integral of sine of 2x is negative cosine of 2x over 2. and I have to remember to evaluate. So we're ending up with x sine of 2x all over 2 plus cosine of 2x all over 4, evaluated from 0 to the power over 4. Okay. When I put in pi over 4 into sine of 2x, well, you get 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. So for the first part, it's going to be pi over 4 over 2, which is pi over 8, plus cosine of 2 times pi over 4 is cosine of pi over 2. Cosine of pi over 2 is 0. So plus 0, minus sine of 0 times 0 is, well, it's obviously 0. And then plus cosine of 0 is 1, so that would be 1/4. Okay, so that will give me pi over 8 minus 1/4 for my final answer. Okie dokie. Shortcuts. There's something called tabular integration that you can use. And it's basically just repeated integration by parts. Okay? So let me show you one that's a repeated integration. So section 5, or I guess section 4, I guess we're on. Let me make sure. Yeah, section 4, doing repeated by parts. And 26, we'll see this x squared cosine of x dx. So you, from Lie, you do algebraic before you do trig. So cosine x dx, du is 2x dx. And then v, the integral of cosine is sine. Okie dokie. This integral then will be u times v minus the integral of v du. So we have x squared sine x minus, I can factor out a 2 integral x sine x. And the issue is we have another integral of a product that we don't necessarily know how to integrate. So you go back to your chart, you say let u be x, dv is sine x, dx, and then v will be obviously negative cosine x, and du is just dx. Okay, so this will equal x squared sine x minus 2 times this times this minus the integral of that times that. So we have negative x cosine x minus the integral of negative cosine x, so that would be plus integral of cosine x dx. Okay, and then that'll equal x squared sine x plus 2 cosine x, and then the integral of cosine is sine x, and then plus c. Okay, great. Is there a way of getting around having to do repeated integration by parts? And yes, so long as one of the functions is kind of annihilatable. Okay, so if you repeatedly take the derivative and one of the functions ends up equaling 0, so the derivative of x squared is 2x, and then the derivative of 2x is 0. Okay? When that happens, you can do this thing called the tabular method. If you've ever seen the movie Stand and Deliver, they show their students doing the tabular method in there. Okay? So anyways, tabular method. We'll do the same problem, but with this method, right? So 26 integral, and we can make it worse. Let's make it x cubed cosine x dx. Okay, so it's like 26, but not the same thing. So what we're going to do is kind of make a chart based off of this process. And what does that end up looking like? Well, you're going to have a chart with signs. So you're always doing this minus thing and then distributing. So it's going to end up with this alternating sign type deal, plus minus, and then you're going to worry about taking derivatives, and you pick the function such that its derivatives will end up being 0. here. So you're picking x cubed and taking its derivative over and over until it's 0. And then you're going to take the integral of the other function and just place that down. And then we have to take products, which kind of mirror what we would have been doing in the charts. Okay, so integral, we start with cosine x, and then the integral of cosine is sine, the integral of sine is negative cosine, and the integral of negative cosine is negative sine, and the integral of negative sine is back to cosine. Okay, so our answer, you figure that out by going like this. It's the positive x cubed times sine x plus negative 3x squared times negative cosine x. Okay, so I'm going to start writing this out. Positive x cubed times sine x minus 3x squared times negative cosine x. So it'll be plus 3x squared cosine x plus positive 6x squared times negative sine x. So it'll end up being negative 6x sine x. And then negative 6 cosine x. So minus 6 cosine x, and then plus your integration constant. Okay, so it's pretty quick, but you do have to kind of remember there's a particular ordering for this chart. Okay. So in my opinion, it's more of a party trick. I never ever use the tabular method in any of my other classes. So I'm not aware of people that actually do. Maybe in engineering, there's some weird place where you would do that, but there it is. You can use it in your homework. If you want to, you can use it on tests. That's fine. Something that does come up, though, is collecting, what I call collecting like integrals. I also call these integrals loopers. Right? So loopers. And the deal is, when you do by parts, you end up back to where you started. So let's look at 45. Integral of e to the x times sine x. And the deal is, if you took the derivatives of e to the x and sine x, they kind of have a cyclical property. I mean, x, the derivative of that is just dx. But if you keep taking the derivative of sine x, you'll end up back to where you started. So I consider those kind of loopers. Let's go ahead and attack it, right? So I need a u, I need a dv. So by Lie, they say use trig before exponential. So my u is sine x, my dv is e to the x dx. So my v will end up being e to the x, the integral of e to the x to the x. du is sine x dx. Here's my chart. I need to go this times this minus that times that, right? So this will be e to the x sine x minus the integral of e to the x, whoops, and this should be cosine x. Okay, so the deal is, once you've integrated here, it don't look like you've gotten anywhere. So you try going by parts again. So in this case, u is the cosine x, and dv will be e to the x dx again. Okay, so v will just be e to the x, and du will be negative sine x dx. Okay, so we apply another by parts to this integral. So we end up with e to the x sine x minus this times this minus the integral of that times that. So it would be e to the x cosine x plus the integral of e to the x sine x dx. Okay? And there's the kicker, right? We've kind of ended up back where we started. So what we're going to do is assign that a variable and then solve out for that variable, because that's what we're trying to find. We're trying to find the integral of that thing. And okay, so what do we have? We have the integral of e to the x sine x dx equaling this material here. And I'll distribute as I go through. So e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. Right, so call this something. We'll call it I. So I equals e to the x sine x minus e to the x cosine x minus I. and then I'll add I to both sides. I get 2 i's equals e to the x sine x minus e to the x cosine x plus your integration constant, and then divide by 2, and that's your answer. Okay, so I would equal e to the x sine x minus e to the x cosine x all over 2, and then plus your integration constant. Okay, so it's the looper. All right. The next section, we're going to be looking at trigonometric integrals. So to prepare us for that, let's see if we can figure out the integral of a trigonometric function that we would normally be able to do. In particular, the integral of secant cubed x dx. So note, previously we could figure out the integral of secant x dx. What is that? That's just the ln of the absolute value of secant x plus tan x plus c. We know the integral of secant squared x dx. That will just be tan x. That one's real easy. Let's see. What's the integral of secant cubed? Is that anything? So we could do by parts. We could split this up because we know these kind of integrals. We're hoping that we could split it up in the secant times secant squared, and maybe somehow we can exploit the fact that we know these to maybe get this. I don't know. So let's see. We'll rewrite this as secant x times secant squared x dx. We'll let u equal the secant x, and then dv equal the secant squared x, because that's the easy integral, right? The integral of secant squared is just tan. So v is tan x, and then du is secant x tan x. So it's kind of like we don't even know if this is going to work, but we're going to go at it, right? And see what we get. So we have secant cubed on one side, the secant cubed x dx, and then it's equaling this times this minus the integral of that times that. So it's equaling secant x tan x minus the integral of secant x tan squared x dx. Tan squared has one of those Pythagorean identities associated with it. 1 plus tan squared x is equal to secant squared x. Okay, so I'm going to exploit that fact to rewrite tan squared x in this integral as secant squared x minus 1. Okay. So this relation will be secant cubed x dx equals secant x tan x minus the integral of secant x times secant squared x minus 1 dx. If you distribute the secant x, you kind of see, oh, I got back to where I started. This is a looper, right? So it's the integral of secant cubed x dx equals secant x tan x minus the integral of secant cubed x minus secant x dx, and it's right there, right? I got back to where I started. So let's call that our I. Secant cubed x dx is I. That equals secant x tan x minus I, and then plus the integral of secant x, which is just ln from our previous work, ln of secant x plus tan x, right? So we knew that integral. ln of the absolute value of secant x plus tan x. And then there's an integration constant floating about. Okay, so add the I to the other side. There's 2 i's over here, and then we get secant x tan x plus ln absolute value of secant x plus tan x, and then plus c, divide by 2, and you get your answer. I is secant x tan x plus ln absolute value of secant x plus tan x, and then that's all divided by 2 plus c, and there it is. Okay, so another integral, we got integral secant, integral secant squared, integral secant cubed. Okay. All right then, thanks for watching. See you next time.